Good morning. This is for section 3.3. We're going to be sketching some rational functions today. I do have two objectives. Well, the first one is just kind of working with the asymptotes of functions using limits. And then the second objective is actually where we go in and graph a whole rational function, identifying x-intercept, y-intercepts. What else? Let's take a look. So I'm planning on dividing this lesson or these videos into two separate videos, where the first one I'm just going to go over how to find different types of asymptotes. So I'm going to go over page 1, 2, and 3 with you right now. 1, 2, and 3. And then I'll come back and go over examples 4, 5, and 6 on pages 4, 5, and 6. Okay? The problem that I will ask you to submit will look a lot like 4, 5, and 6. But then your homework on my math lab will have a lot of these, just simply finding asymptote problems. Now, you've seen these asymptote problems in Math 161 in pre-calculus class, but just kind of wanted to revisit them so that when we get to the graphing part, we can graph all these and we can talk about where the function is increasing, decreasing, concavity, all that calculus. But let's first go over asymptotes, okay? All right, first let's define a rational function. A rational function is a function if, and that can be described by a ratio of two functions. So let's write down P over Q. So f of x is going to be a ratio of two polynomial functions where P and Q are polynomials with Q is not the zero polynomial. Just like how in a fraction, we're not allowed to have 0 in the bottom of the fraction. So Q of 0 cannot be 0. Okay, Q of x cannot be 0. Okay, when we ask to find the domain of these rational functions, remember we simply find the excluded values, and the excluded values are going to be whatever the x values that will make the Q of x 0. And this really connects with the vertical asymptote. You learned that in order for you to find a vertical asymptote of f of x, you did in pre-calc, okay? We set the denominator equal to 0. And, there is another, because that one will not only find denominators, we may be able to find wholes if you use that method. So what I prepared was, well, first ABC, and I think ABC and like D, that method will work just fine. If I ask you to find the vertical asymptote, we will set the denominator equal to 0, and that's how you can find the equation. But there is something else called whole. And a rational function may have a whole, and we'll look at a graph together. I have a Desmos app on my iPad, so I'll be able to graph one with you and then see how it's really not a vertical asymptote, even though it is a 0 of a denominator. So we'll look at those cases. But, well, let me give you the definition in our class. And using limits. Remember when you graph these rational functions, it's wherever, suppose that I have a vertical asymptote at positive 2. Okay. And then maybe just, let me sketch a graph here. Vertical asymptotes are where the function kind of does that funky little thing. It's going to try to approach that asymptote, but it's going to just curve up and go straight up to positive infinity, or it may just go straight down to, it's going to try to get really, really close to that line, but it won't be able to cross that vertical asymptote. So that's, instead, they just kind of curve up all the way to positive infinity or down to negative infinity. So that may happen. So let me fill some of these blanks out with you. Say that our A here is 2. X equals 2 is the vertical asymptote. As our graph, my pink line is approaching this a or x equals 2 from the left side, notice that it's going up to positive infinity, right? As my pink graph is approaching 2 from the right side, this is going to negative infinity. So doesn't matter which direction it is approaching that vertical asymptote. Look at this notation as x is approaching a from the left. F of x is either going straight up to positive infinity or straight down to negative infinity. And this part right here is x is approaching a from the right. The function value f of x is going straight up to positive infinity or negative infinity. And if any of these statements are true, then, that's how we find these vertical asymptotes given the graph, right? So that's the definition, and we can find these vertical asymptotes using this. But I think all the examples that I'll go over with you today and the homework problems, our old methods still kind of work. So let me highlight that old method that we're going to be using down in our example 1, okay? So we'll start with this. We're going to find the zeros of the denominators. To find the vertical asymptote, find the zeros of the denominator. Okay? Okay, so let's find some vertical asymptotes. Example 1, determine the vertical asymptote or asymptotes, because a function may have more than one vertical asymptote of each function. If none exist, we're going to state that fact. Okay, so I got A, B, C, D, E, F. Some of them will have one vertical asymptote, some will have two, some may have none. So let's start with A together. So to find the vertical asymptote, grab that denominator. Now before we go there, let's be a little careful. Make sure your expression simplified all the way. Now, is there anything that I can cancel out? Is there anything that I can factor? Not really, right? Now, this expression is completely simplified. So what I can do is I can grab that denominator and set it equal to 0. X plus 4 equals 0. So I have a vertical asymptote at x equals negative 4. This function has one vertical asymptote at x equals negative 4. Okay? Let's look at another one. Oh, notice I was about to grab this denominator, but it's not exactly factored out just yet. So it will be nice because I will show you where the holes may happen. So try to rewrite this h of x by simplifying first, okay? By factoring to simplify. So the numerator is still x minus 5, but if you factor the denominator, you will get x and x. What times what gives you 25, but they add up to 10. It's got to be positive 5 and another positive 5, right? Now, does anything cancel out? Yes or no? No, nothing cancels out, right? So if nothing cancels out, you're ready to just grab that denominator and set it equal to 0. Let's find the zeros of the denominator. So if you have x plus 5 times x plus 5 equal to 0, they're exactly the same factor, right? So we have a vertical asymptote at x equals negative 5. So one vertical asymptote at x equals negative 5. Okay? All right, let's look at C. Oh, okay. Now, we're going to have to factor this g of x first, the denominator. Let me simplify this. So x minus 2 stays on top. But let's see, what do they have in common? They all have x in common, right? So let me factor out x first. Factor out the x first. We will have x squared minus 4x minus 21, right? Let's see if we can factor this anymore. Yes, we can. That's a trinomial. in the denominator. So keep that x minus 2 exactly the same on the numerator. And I ask you to do that because there are going to be cases where things will cancel out. And if things cancel out, we're not going to be able to call them vertical asymptotes. We're going to have to call them whole, okay? So still write it. Now x is still in front of it. But now let us factor this trinomial, okay? Let's factor that trinomial. What times what gives you 21? 3 times 7. Now, in order for us to make the negative 4 in the middle, let's make the 7th negative, positive 3 right there. All right. Now, look on the numerator and the denominator. Does anything cancel out? Not really, right? No factors cancel out. So let's find all the vertical asymptotes. Vertical asymptotes are the zeros of the denominator. And we have 1 factor, 2 factor, and 3 factors here. So we're going to have 3 vertical asymptotes, okay? The first one is at x equals 0 for that guy, right? What's the second one? Negative 3, and that's for that factor. And the last one is going to be positive 7. So this equation, this rational function will have 3 different vertical asymptotes, okay? Now let's go down to D. Okay, D. Let's see if we can factor the denominator. Now, is this factorable? Factorable? And the answer is no, right? If you have x squared minus 9, if you have difference of squares, you can factor it into x plus 3 times x minus 3. But this is not a difference of squares. This is a sum of squares, right? Sum of squares. So don't try to factor this. We're not going to be able to factor this. So, well, let's just grab this and set this equal to 0 then. And let's try to solve this. X squared plus 9 equals 0. Subtract 9 from both sides. You'll get x squared equals negative 9. Now we notice something's weird here, right? What kind of number can you square and get a negative 9, right? No real number, right? So you say that you take square root of both sides and realize, oh, square root of negative 9, that's gonna, well, if you try to solve this, this will give you x equals plus or minus what? 3i. Now, a vertical asymptote, we're going to be able to graph it really, right? So how will you graph a vertical line at positive 3i and a negative 3i? So this equation has no real solution. We have no real solution. So what we're going to tell them is that n of x has no vertical asymptote, okay? Now, I do want to see what it looks like. So let me try to graph this with you. I'm trying to use my cell phone to take a picture of this function so that I can get out to my Desmos app and graph it. So let me open a graphing calculator app. Got all these math apps that I downloaded. Let me go ahead and graph the one that we just solved. Let me type in x minus 3, close parenthesis, divided by x squared plus 9. If I graph that function, first of all, where is my function? Oh, here it is. Now you see it's just a nice looking line, just a line. And to be a vertical asymptote, my function needs to approach positive infinity or negative infinity as this graph approaches a number to the left and right. But I really don't see anything. See, this function does not have a vertical asymptote. So yeah, so graphically you can just kind of graph it and see. But I do want to come back and graph a couple other vertical functions as they will have holes instead of vertical asymptotes. So this function, you know, both algebraically and graphically, we did not find any vertical asymptotes. All right, let's go back to P or E, the P of x. Now this one is going to be a little special, okay? This is going to be a little special. Say that it will be wrong for you to say that we have a vertical asymptote at x equals 3. That's going to be incorrect. Okay, that's going to be incorrect. Let's see why, okay? So first factor, P of x. Then, well, notice the numerator, x squared minus 9 can be factored into x plus 3 times x minus 3, right? So, I mean, in pre-calc in 161, probably all the examples that we went over, unless you took math 3, because one year I taught math 3 in North Carolina. I think those guys, they had to know the difference between whole and vertical asymptote back in math 3 before they go into pre-calc. But I just don't think math 161 that I went over, we didn't really look at holes, but we're about to see one here, okay? Now keep the denominator exactly the same, the x minus 3. Now, do you see what happens here? What will happen to that x minus 3? That will cancel out. This will actually cancel out. So we won't be able to find a vertical asymptote. What we're going to say is there is no vertical asymptote. But do tell them, but we have a hole at x equals, what number do you think? 3, okay? So let's take a look at that. We're not going to have a vertical asymptote here because the factor that will make the 0 of the denominator just really canceled out. Oh my goodness, my eraser is just way too big. So let's graph this function, p of x, and I'll show you what why this makes sense, okay? So I tend to forget things easily, so I'm going to take a picture of that so that I can go to my Desmos app. So let me graph that function with you and show you that this function does not have a vertical asymptote. The numerator was x squared minus 9, and the denominator was x minus 3, right? Okay, so I graphed it. Now let me zoom out, or just, is there a way for me to just zoom in standard screen? Okay, yeah. Because I messed with the y-axis earlier. Now, does it look like a rational function, or a typical rational function that has a curve and that kind of has that invisible vertical asymptote line? That, you know, it really doesn't. You know what it looks like? It looks like a linear function, right? It looks like a straight line function. So what we can do is, remember we said that we're going to have a hole at x equals 3, right? So take a look. I'm going to try to approach 3. I'm going to try to approach x equals 3. Now look at my point. All right, come on. Look at my point here for me. I'm trying to approach 3, x equals 3. Da, 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 da. And as I get close to 3, oh, I'm going to have to go up like here. It looks like this function is continuous, don't you think? I would say this is almost continuous, but as you see, as I'm going to 3, oh, did you just see that? Look, at x equals 3, what does it say? Oh, gosh. I keep moving, so I don't know if you can see that. At x equals 3, the function is undefined. Oh, so you see how the graph just kind of gave me an open circle right there? So if you are graphing this, you're going to graph this function. And you know what? Let's copy this function on our paper too. We're going to have a hole at x equals 3. And the y value of this hole is what? 6, right? So we have a hole at 0.36. Let me come back to my graph. So if I do a quick sketch of this, it's gonna be a linear function. This is how you can graph this. You can graph y equals, and let me show you where I'm grabbing that. You can graph this, y equals x plus 3, but make sure to plot a hole at, not hot, plot a hole at 3, 6, okay? So it's gonna look like that. We go 1, 2, 3 up to plot a y-intercept. And as you go 1, 2, 3 to the right, 1, 2, 3, 4, 5, 6, we're gonna have a hole right there, an open circle. But other than that, this graph will look just like a linear function. So this is that's the graph of it, about p of x. And notice that, you know, although x equals 3 was a 0 of a polynomial, when you simplify this, it cancels out. So it's not going to be called a vertical asymptote. And you can see how it doesn't, around x equals 3, our graph doesn't behave to go up to the positive infinity or negative infinity. In fact, their limit was actually, the left limit and the right limit was 6, right? So this is not a vertical asymptote. So I just wanted to give you a case where if it cancels out, it's not going to be called vertical asymptote. In fact, it's going to be called a hole. Okay, let's try the last one, F, right here. Let me try to zoom in. Okay, so first thing that you're going to need to do is factor. Okay, to see if we can simplify. The numerator, if you look at the numerator, we have x squared minus 2x. I can factor out x because they both have x. Then I will have x minus 2 left inside. I'm done with the numerator. Now let's look at the denominator. The denominator has x cubed minus x. So what can I factor out? I can factor out x. Then I will have x squared minus 1, right? This is also factorable again. Q of x is x times x minus 2 over x times, notice this is a difference of squares. X squared is a square, 1 is a perfect square, so I can factor that into x plus 1 times x minus 1. Now I am done completely factoring this. I should be able to see if anything cancels out. Any common factor? Yes, the x will cancel out. So what do we have? We have a whole at, I keep saying whole at x equals 0, okay? Because, because this canceled out, x equals 0 is going to be the whole. But now we have two vertical asymptotes. Vertical asymptote at x equals -1 and +1. So that's how you can find vertical asymptotes, and it was a little special because we were able to see some of these zeros of denominator doesn't exactly make it a vertical asymptote. Instead, they made a hole when they get canceled out. So that's enough of finding or playing with the zeros of denominator. Let's look at the second type of asymptote called horizontal asymptote, okay? Now, in pre-calculus in Math 161, you looked at horizontal asymptote by cases. Now, remember that n equals the degree of the numerator and m equals the degree of denominator. And what we did was we did it by cases. So let me just write down what you learned in pre-calculus. Case 1, if n is greater than m, if the degree of the numerator is greater than the degree of the denominator, then we had no horizontal asymptote. That was one of the cases. Now, case number 2. What if n is smaller than m? Now, this is the case where the bottom degree is bigger. If that was the case, we had a horizontal asymptote at y equals 0, right? Now, the third case, what if they are equal? If n equals m, then the horizontal asymptote was at the ratio of their leading coefficient. So, leading coefficient of the numerator divided by leading coefficient of the denominator. So that's what you did in Math 161. That's how we found horizontal asymptotes, case by cases. But since we know how to find or evaluate limits at infinity, we're going to use the calculus definition of horizontal asymptote. So let's go ahead and fill out the definition here. The line y equals b is a horizontal asymptote of f of x if either or both of the following statements are true. So they don't both have to be true. And in many of the cases, they are going to be both true. But as x gets really, really, really small, as x goes, well, that's what it is saying, is x going to negative infinity as the graph goes to the left, okay? This is the left end behavior. As this graph goes to the left, the function value is approaching a value, b. And this right here, as x approaches positive infinity, that they're talking about the right end behavior. So in the picture, it's going to be very simple, something like this. Say that I have a horizontal asymptote at 1, 2. Just kind of making it up. Say that I have a horizontal asymptote at 2. Your graph is going to look like this. So it's going to come down and it's going to try to approach that y equals 2 as x is going to positive infinity. And this other side, as x is getting really, really small, as it's going to the left side of this graph will approach the y value of 2. So if you see that, that's going to make it the horizontal asymptote of this rational function. So you can, I think if whatever your method you're comfortable with, you can go ahead and just use these degree thing, the 1, 2, 3 that we talked about in 161, or you can try to do the limit if you want to, because you do know how to do both methods. I have 4 examples to go over with you. The 4th one, you're gonna have to use that limit definition. So you know what? Let's kind of do what we did in pre-calc. Okay. Look at the degree of the denominator and the numerator for f of x here. Degree of the numerator is 1. Why? Because this is 2x to the first power. The degree of the denominator, m, is equal to 1. So if they are the same, this is case number 3, right? You just have to take the ratio of their leading coefficient. And if you don't see the leading coefficient of the denominator, you see it's just simply 1x, right? So we do know already that the horizontal asymptote is at y equals 2 over 1. So horizontal asymptote is at y equals positive 2. Now we did this using limit before. We just never called it the horizontal asymptote. I just asked you to evaluate the limit. So why don't we do this, the limit method? That has a good review. That's by using cases, what we just did. But let's take the limit as x approaches positive infinity, okay? I just picked positive infinity. It could be negative infinity. It doesn't matter. But you have 2x minus 1 divided by x plus 4. Remember the little trick? What did we do here? We will multiply every term by 1 over x. Okay? Okay, so what's that going to be? That's going to be limit as x approaches positive infinity of 2x over x minus 1 over x all over x plus 4 over x. Now we're going to simplify this. That's the same thing as limit as x approaches infinity of 2 minus 1 over x, 1 plus 4 over x. Now what I'm about to circle, you see these guys? You know what they are, right? They just go straight to 0, right? So if you evaluate this, that's going to be 2 minus 0 over 1 plus 0. Therefore, the limit goes to 2. So both methods are fine. The bottom that I just did with you, that's using the limit definition of horizontal asymptote. But you are more than welcome to just go with the case by cases if you want to. But B, look at B. Let's try this one. This one's a little different because you're going to have to rewrite your g of x first. So make this into a single rational expression, okay? So let's first combine these 3 minus 2 over x into a single fraction. What I'm going to do is I'm going to multiply this 3 by x over x. So let's write it as 3x over x minus 2 over x. So that I can actually simplify or subtract these denominators and write it as 3x minus 2 over x. Now we can see that the degree of the numerator is n equals 1 and m equals 1. So if the degrees are the same, we have a horizontal asymptote at the ratio of their leading coefficient. And as you can see, their leading coefficients are 3 and 1. So we have a horizontal asymptote at y equals 3. Now, what we can do is we can still do the limit definition or limit way. Limit is x approaches positive infinity of g of x. Let's find what that is, okay? Just kind of showing you two different methods. Why not? Let me keep the exact same format. 3 minus 2 over x. Remember, one of the limit property that we know is that we can separate this into a two separate limit. I can write this as limit as x approaches infinity of 3 minus limit as x approaches positive infinity of 2 over x, right? What's this just going to give us? That's just going to give you 3, right? Because this is a constant function, and if you plug in x equals infinity, well, it's still going to be just 3. No matter what x value is, the function value is just at 3. So that way, that one, I think is it was the constant property, I think. And now what about this one? What about this one? That will give you what? 2 over infinity, and we know that's going to be just 0. So that way we can still get y equals 3. Up to you, whichever method you use. I think the case by cases are easier, but you may have to use the limit way on a problem like D. Well, let's try one more, C, where both methods will work. Now, I do want to talk about this here, though. Well, not really. This isn't any different from the ones that we were doing. All right, let's see. Now, what is the degree? Because this is already written out in standard form. I can tell that the degree of the numerator is n equals 3, and the degree of the denominator is m equals 4. So, well, which case was it? This was when n is less than m, and if that's the case, then we have oh, I wrote the wrong thing. If this is the case, what we're going to say is that we have a horizontal asymptote at where y equals 0. So as simple as that, if you know all your cases, that's enough. That's really enough. If n is less than 0, if n is less than m, then we have a horizontal asymptote at y equals 0. But you want to see why that's true? Yeah, let's see that. Let's see why. Let's plug in the limit. Okay, let's do the limit. Limit is x approaches positive infinity of my 4x cubed plus 5x squared over 5x to the 4th minus x plus 2. Now, what are we going to multiply everything by? We're going to multiply every term by 1 over x to the 4th. Okay, 1 over x to the 4th. So if you do that, that's going to be limit as x approaches positive infinity of 4x to the 3rd over x to the 4th plus 5x squared divided by x to the 4th over 5x to the 4th over x to the 4th minus x over x to the 4th and plus 2 over x to the 4th. It looks super fancy what I just did, but all I did was I just put x over x to the 4th all over all these terms. Now let's simplify this. Limit as x approaches infinity. So the first term, if you look at this one, what's that going to turn into? That's going to be 4 over x, right? Next one, plus 5 over x squared. Go to the bottom of the fraction. This will just turn into 5 minus 1 over x to the 3rd. And then last one, plus 2 over x to the 4th. Okay, now let's evaluate the limit. Now, I'm about to circle some of the things that will just go straight into 0. That's going to turn into 0. That's going to turn into 0. That's going to turn into 0. What else? That's also going to turn into 0. So if I rewrite this, that's going to be 0 plus 0 over 5 minus 0 plus 0. That's 0 over 5. And what's that going to be? 0 over 5 is simply 0. So we do have a horizontal asymptote at y equals 0. So that's how you can use the limit to find the horizontal asymptotes. As x gets really, really, really big, this function will approach the y value of 0. And it's going to be almost exactly the same thing if you work with the negative infinity, okay? Alrighty, let's look at the very last one, okay? D. And because I think the slant asymptote will go kind of quick, I think I'm almost done with this first video. D, ooh, see, the degree game doesn't work for this guy because this isn't really, I don't know why I have this random exponential function stuck in this section because I wanted to just go over the rational functions, but it's okay. Why not? Let's find the horizontal asymptote, okay? gotta use the limit, right? Because there's no degree of the numerator or there's no degree of the denominator. So limit as x approaches positive infinity of no. You know, I think it would be better for us to use the negative infinity. But let's check both because let me show you something. They said if either or both of the following statements are true, right? Either this is true or that is true. I think I'm going to do both of them. I'm going to do both of them in this case, okay? All right, let's do the positive infinity first, okay? Because I think we're going to get two different answers here. Alrighty. Anyways, limit as x approaches positive infinity of 2 times e to the 4x. Haven't done like limit calculation in a long time. So let's see. We can pull out different things, but just imagine plugging in infinity into x here because, you know, we can think about it that way. What will happen if x is a very, very, very big number? What we're going to have is that exponent is going to be just extremely big, right? So I really don't want to write this, but I'll write it. What is going to be 2 times e to the 4 times a really, really big number? Oh, I really don't want to write this, but I will. Because that's not what we're doing. Let me use my calculator to figure this out, okay? 2 times e to, we don't really need a calculator for this, but let's try that. What if we do 2 times e to the, oh dear, I forgot what the number was. It was 4x, okay. Hold on, let me turn off these ads, all these free apps that I download. They have all these apps. No, okay. 4 times a really, really big number. All right, what's a really, really big number that you want to plug in? I'll do 1,000. No, that's 10,000. All right, if I hit enter, it's going to say, oh, it's too big, Sue. Okay, maybe I'll just do like, oh no. See all these free apps that I downloaded, they make me go through these, get a free sighting estimate, huh? Delete, undo. Maybe just 100. Maybe that's big enough for you to see. Now, it's so big, they use a scientific notation, you see? So, just want to show you that as the exponent gets really big, because e is nothing more than a number, right? E is just a constant, 2 point something, 2.14 or 2 point, no. So, if the exponent gets really, really big, this term will just go straight up to positive infinity. The y value will just get really big as we are approaching the positive infinity. So to the right end of this graph, we're just going up like crazy. Let me try one more. 4 times, maybe I'll just make it like small, like 10. If x is only 10, notice it's still really big. E to the, so you move this 17 to the right, this decimal place 17 to the right, it's already super big. 4 times, maybe just 5. Will that be enough? Let's see. If x is only 5, this number is like 970,330,000. So I think you've seen enough where if this is true, then what's the limit? It's just going to go up to positive infinity. And I can't say that we have a horizontal asymptote at y equals positive infinity because no one is going to be able to graph that, right? How are we going to graph it? So this is where I give up on my positive guy, because it just gave me positive infinity. Now let me try the negative infinity. Y approaches negative infinity of 2 e to the 4x power. Now let's see what that's going to give us. 2 raised to the e times 4 times, well, this is going to be a really, really small number this time, right? I feel silly writing this, but that's the idea. You're plugging in a really, really small number in negative infinity into x. So let's see what will happen. We can just plug in a couple examples to see, but I want to talk about y. Going back to my calculator, this time let me do 2 times e to the, not that, 2 times e to the 4 times, give me a small number. Let me do negative 20. That's a small number, right? If I hit enter, Okay, so maybe that wasn't, that was just a little too small. So I just want to show you a number. Maybe I will do like, but you see what they're doing? You're going to have to move this decimal place, what? 35 to the left. So we're really approaching 0 here. But let me show you one more. What about 2 times e to the 4 times? Let me just do like -4 or something. That's small enough. Oh, it's too small for them. This calculator, I don't think I will leave a good review for this app. Because I want these scientific notations written out. Maybe let me just do like -2. That's not small enough. But you see, where do you think this is going? It's never going into negative infinity, a negative number. But this is really approaching 0. It's going to be very, very small number. Now, let's see why, okay? Because that's going to be, well, this part right here, that's going to give you a fraction. That's going to be dividing a 2 into a really, no, I'm not going to go there. Well, what can I do? Oh, I can show you a graph to convince you. If that plugging in numbers didn't really convince you so much. Let's graph this and see why this is true, okay? Just a quick, yeah, let's graph this on Desmos. Let me graph y equals 2 times e to the, I wonder if that will take that e as a 2 times e to the 4 times x, right? Now that's the graph, guys. That's the graph. And as you can see, let me try to change this. I wonder if I can change just the y-axis. I just want to zoom out on the y-axis. But as you are going to the right side of this graph, you see how this graph is just going up like crazy? That's what we saw on the first time when we plugged in positive infinity. This graph is just increasing without bounds to the right side. So that makes sense why we got positive infinity when we plugged in positive infinity. But now go to the left side or left end of this graph. Where do you think this function is approaching? It's going down, right? This, as you go to the left side, it's going down, but it's never crossing the x-axis to go down to the negative, right? Can you see clearly that this graph is approaching what number? 0. So that works. That really works. Or maybe just want to try all my... Let me try this. Let me try to go back to a graphing calculator and... show you the y values or the values. The 2 times e to the 4x power. Let me graph that. Now we already kind of graphed it together. I wanted to show you the xy table. But this one, it's clear to me that y is just going to 0 as we're following this graph to the left. But I wanted to see the table, if that will let me. Table set. Let me make the table to start at maybe like negative 2, and then I'll make the table to go up by like 0.1. And let's see, that will be enough. Table put, I don't know. I want to see the table. Okay, all right, that works. So take a look. Maybe I should start from somewhere like this. As x gets really big, you see how the numbers are getting, the y values are getting big, right? Only at x equals 2. My y value is all the way up at 5,961.91. See, as x gets really big, the function value is just going straight up to positive infinity. Now let me go down to smaller number. Let's go to the negative. As x gets really small, I'm getting smaller, right? Look at the y values. What are they approaching? Now they're just becoming a smaller and smaller decimal, right? Smaller and smaller decimal. But are they ever going to the negative number? You see, it's just getting closer and closer to 0. And at that point, at negative 2.5, it's so small, this calculator started pulling those scientific notations. But as you can see, none of them will have a negative symbol. So, enough of that. I think I talked enough of it. You can see both algebraically and graphically, or well, I should say numerically, because we just plugged in. This limit is 0. So what we're going to say is that this function has a horizontal asymptote at y equals 0. Okay? All right, because either of these had to be true, even though they didn't really agree, it does have a horizontal asymptote to the left side, and that line is going to be at y equals 0. Okay? All right. Let's try the very last asymptote called slant asymptote, and that will be it for this video. I'll come back and do example 4, 5, and 6 in another video. A definition: a linear asymptote, a straight line, a diagonal asymptote may happen. That is neither vertical or horizontal is called a slant asymptote, or sometimes an oblique asymptote. Okay? For any rational function of the form, regular are rational function where we have a ratio of two polynomial functions. But, you will only have a slant asymptote when the degree of p of x, the top, the numerator is exactly one more than the degree of q of x. Let me give you examples. I'm going to make up some examples so that that's clear to you. Maybe you may have a function like this. F of x equals x to the 56th power plus x divided by x to the 55th power minus 3. Now, I made it extreme just so that you can see what they mean by the numerator degree has to be exactly one more. Degree of the numerator is what? 56. Degree of the denominator is what? 55. Notice 56 is exactly one more than 55. In that case, yes, you're going to have a slant asymptote. It's not, maybe another one. Like, how about g of x? That equals x to the x squared minus 5. And the denominator is just x plus 1. The degree of the numerator is 2. Degree of the denominator doesn't say it, but it's just going to be 1. So because 2 is exactly 1 bigger than 1, you will have a slant asymptote. Sometimes you just don't have it. If the degree in the denominator is bigger, then you're not going to have a slant asymptote. If the degree of the numerator is bigger by anything other than 1, you're not going to have one. So let's look at these 4 cases. What is the degree of the numerator? Degree of the numerator is 1, right? Because f of x is 3x minus 4. So the degree is 1. What about the degree of the denominator? Again, that's going to be 1. So, is 1 bigger than... You see, this is not going to have no slant asymptote. Because, well, first of all, the top has to be bigger, and they're exactly the same. So since they're the same, we're not going to have a slant asymptote. You will have, what's it called? The horizontal asymptote at y equals what number? Y equals 3. But this one will not have a slant asymptote. All right, let's look at the next one, B. The degree of the numerator is 1, and the degree of the denominator is 2. Now, some people may think they have it because 2 is exactly 1 bigger than 1. But remember, the top has to be bigger. This has to be bigger. Now, 1 is smaller than 2. So what will you say? This one has no slant asymptote. What kind of asymptote will it have, though? It's going to have a y-intercept, a slant on a horizontal asymptote at y equals 0, right? Because the degree in the denominator is bigger. All right. But I better show you at least 2 cases where they actually have a slant asymptote. And what if you decide that it's going to have a slant asymptote, how are you going to find it? So I'll show you C and D. They will both have a slant asymptote. So take a look. C. Degree of the numerator is 2, right? What about the degree of the denominator? It's going to be 1. Oh, you just saw that 2 is exactly 1 bigger than 1. So this is going to have a slant asymptote. So how are you going to find this? You're going to find it by actually doing the division, okay? Up to you, a polynomial division, a long division, or synthetic division. Let me do the long division here. Do the long division. I think synthetic's just easier for me, but at least I want to show you one case where I used a long division. Let me set this up. But you see it was x squared going straight to -4, and it was missing a linear term, so I stuck in that plus 0x right there, okay? So let's go ahead and do this long division. Divide x squared by x. That's going to be x. If I multiply x2, these two, I will get x squared minus 1x. Okay? All right, good start. Now let's go ahead and subtract this from the line above. X squared minus x squared is 0, so that terms gets canceled out. But if you do 0 minus -1, if you do 0 minus -1, that's going to turn into plus 1x, right? Bring down your -4. And then we're back to dividing. Divide 1x by x. Well, x divided by x is simply going to be 1, right? And you know, at this point, we found the, what's it called? The oblique asymptote already. Because the slant asymptote is simply going to be the quotient of this long division. But we can try to finish this. If I multiply 1 to x minus 1, that will just be x minus 1. And then I'm going to subtract these two lines and get 0, and then -4 minus -1 will turn into -4 plus 1. So the remainder is going to be -3. Now, when you do the slant asymptote, you don't really care about the remainder. The slant asymptote is simply going to be the quotient of this division. So we have a slant asymptote at y equals x plus 1. Okay? So something that you probably saw already in Math 161. But if you decide that, oh, this function will have a slant asymptote, what you need to do is you just have to do the division. It doesn't have to be long division. You can do synthetic division if you want. So for D, let's probably do that. Now, what's the degree of the numerator? 2. What's the degree of the denominator? 1. So this is the case where we're going to have a slant asymptote. So let me do synthetic division on this one. Up to you, whichever division you like. I'll put my 3 in my little box, write the coefficients of 2, 1, and -1 outside. Bring down the 2, nothing to do with that 2. Multiply 3 times 2, and then add. Multiply 3 times 7, and then add. Now, this is the remainder, right? So we don't really need the remainder. But if you rewrite the quotient, we have a slant asymptote at y equals, what's the equation? Y equals 2x plus 7. Okay, so that's what you can do. You can do the synthetic division if you want. And if I just do the synthetic division over here for C, just one more time, just to try another division, I can put 1 in the little box because I'm dividing by x minus 1. And then put 1 for the x squared, 0 for the x, -4 for the constant. And I think this is just a little bit easier. Add, and then I'll get 1 plus 1. Well, no, 1 times 1 will give me 1, and then add and get -3. So -3 is the remainder, and you know how that matches what I got from doing the long division. And the quotient is going to be what? The quotient is going to be y equals 1x plus 1, and that matches what we got over here too, right? So up to you if you want to use long division or synthetic division, but you only do that if the denominator, if the numerator degree is exactly 1 greater than the degree of the denominator, okay? So that took me a little while to go over all 3 types of asymptotes, but in the second video that we will go over in a bit later, I will go through example 4, 5, and 6, and the classwork problem that I will ask you to submit today or this week will be similar to these 3 examples, okay? So please come back and watch 4, 5, and 6 and for your classwork problem.